Now let's look at problem set 3 here for a minute. And with problem set 3, I got some really great news. To set the groundwork for the great news, I want to go back to this problem that we were looking at right over here on problem 2 in the previous video. Do you notice what happened right here in part D, where we were taking the square root of a negative 2 squared, and then the correct answer actually was a positive 2? What is going on right there is it's covering this scenario here. Is if we were trying to take a square root of that's a horrible looking x. Let me grab the pen instead. If we were trying to take a square root of a number, some unknown number, or any type of root for that matter, of an unknown number, and we weren't quite sure whether that number that was there was positive or negative. Since we wouldn't know what that number was positive or negative, the answer that we end up getting, this guy right here, this 2, is actually the absolute value of that number. Okay? The same kind of situation happened right down here when we looked at the square root of negative 7. So the bummer part is when we're looking at a variable, we aren't quite sure. See that A that's right there, now that you're on the other side of this note sheet, we aren't quite positive if that number there, no pun intended, if that A right there is a positive number or a negative number. And because we don't know that, there's two situations that could happen. Either the answer is just simply A if we're taking an odd root, or the answer is the absolute value if that root is even. So that's the groundwork. The good news that I'm going to tell each and every single one of you here today is we are not going to work with any of those rules at all, period. So pretty much here's what I'm trying to tell you here. See this spot? Got your pencils ready? I want you to simply get rid of that whole braced group and that separation right there. And what I want you to think about is that if I ever have to take the nth root of any number raised to the same power, the answer is always going to be A. In other words, we were always going to assume that all variables are positive. So we'll go ahead and write that down. We are going to assume that all variables are positive. What that allows us to get away with doing, and I've seen many different textbooks do this. I mean, it's really not that uncommon for work with radicals to have the situation where if I were to ask you, hey, what is like the fifth root of, if we said 7 to the fifth power? Well, the fifth root of 7 to the fifth power, since fifth roots and fifth powers are inverses of each other, they end up undoing each other, and your answer is just simply 7. So that's pretty much what we're trying to say right here, is that the nth root of a to the nth would be equal to just simply that number that's underneath. Okay? That's all that's saying. Period. So let's do that and use that nice little caveat to help us solve some problems pretty quickly here. And so basically what I'm kind of just telling you, see all this junk that's over here, go ahead and cross that off because we aren't going to be worried about any absolute values. In fact, if you go to your your homework log sheet and you look at the 6-1 homework problems I assigned, I make another note right there too, is that you don't ever have to write down absolute value bars for any of these answers here. Okay? Okay? Okay. So let's take a look at these problems right here. So problem 3, let's write a simpler form of each one of these radical expressions. Let's still work underneath this premise that all the variables that we're working with here are positive numbers and not negative numbers. And take a look at how the textbook tries to go about explaining to you why the square root of 16x to the 8th is all the way just to simply 4x to the 4th. What they're doing is they're breaking apart the 16 and breaking apart to the x to the 8th into perfect squares so that way they can use that property right there of square roots canceling out squares. Okay? I got another plan. Okay? Think about this property here. And that is, do you remember when we were dealing with square roots and I showed you this little property just like this? If I took a square root of, say, two numbers that are multiplied together, remember we did that when we were working with, say, like the square root of 12. I had you break that apart into the square root of 4 times 3. Didn't that allow us to do this little move right here, the square root of a times the square root of b, and just do each square root individually? So the square root of 12 could be written as the square root of 4 times 3, which would allow us to write the square root of 4 times the square root of 3, which would allow us just to simply say 2 square roots of 3, right? Right? Right. So let's use that same principle on this problem here. Instead of looking at this problem, and I encourage you to do that on all these homework problems and on quizzes as well, is instead of trying to break it down into this type of logic with square roots of squares or cube roots of cubes, instead break it apart just like this. When you're trying to take the square root of 16x to the 8th, think of that as two factors multiplied together. Can we look at that as simply the square root of 16 times the square root of x to the 8th? We can look at those as two individual square roots, and then we can just take the square root of 16, which would be, you got it, 4. And now the square root of x to the 8th, can you think of an x variable that when I multiply by itself 2 times, I end up with x to the 8th? I think I could do that if I have x to the 4th, right? X to the 4th times x to the 4th would give us x to the 8th. Remember our little product property is that we would add those exponents up, right? 4x's multiplied by 4 more x's would be 8x's multiplied together. Okay, so if we have 4 times x to the 4th, and what shorter way of writing that without the dot would look something like that, 4x to the 4th. Nice, right? Let's take a look at the next example. The only difference now is we're dealing with cube roots. But guess what? The rules are no different. I have two things being multiplied together here. A to the 6th times b to the 9th. So couldn't I separate that and use my that cube root and separate that into the cube root of a to the 6th? And let's multiply that by the cube root of b to the 9th. Now that we're dealing with cube roots, we're trying to come up with a quantity that when we multiply by itself 3 times, we end up with the number underneath the radical. So a to what power times a to the same power times a to the same power 3 times would give us a to the 6th. I think we can do that with a squared, right? And then I think we can do the same thing if we have b to the 3rd times b to the 3rd times b to the 3rd, right? Because 3, 3, 3. Add up those 3's, we end up with a 9 for the exponent, okay? So there would be that answer. Are you noticing a trend here? Are you noticing a connection between these guys and those guys? I'm going to come back to that in a second here. Be prepared. And so let's look at the last guy. 4th roots now of x to the 8th times y to the 12th. Why don't we just split that one apart too? We could look at that as the 4th root of x to the 8th times the 4th root of y to the 12th. So blank, 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 1, 2, 3, 4, 4 groups of x's multiplied together to get x to the 8th. I think we can do that if we had x squared, right? And then 3 y to the 3rds multiplied together would give us y to the 12th. Well, I'm sorry, 4 y to the 3rds multiplied together would give us y to the 12th, right? So here's the question I want us to think about here, just for a second. Is that, are we noticing a pattern here? Let's look at these two examples. Do you notice a pattern that whenever we try to take an nth root of a to the m, in other words, this guy right here, and then that answer right there, do you see a connection between the 3, the 6, and the 2? Or do you see a connection between, let me reverse that, the 9, the 3, and the 3? Do we see a connection between, now you see how these are square roots like that? Think of that as being like a little 2 right there, or a little 2 right there. But I'd like you to focus on this guy right here. Do you see a connection between the 8 and the 2 and the 4? You've got it. It's just simply equal to you taking that m, that number that's in this guy's place, and dividing it by that number that's in that guy's place. Pretty awesome, right? Yeah, I know. Let's use it. Let's use this. Take a look at these examples. See if you can come up with the square root of 81x to the 4th. See if you can come up with the cube root of a to the 12th, b to the 15th. And then see if you can come up with the 4th root of x to the 12th, y to the 16th. Okay? Let's pause this video, go ahead and split those apart, and take square roots of each one of those. For a, split those two apart, take the cube root of each one of those, and take the 4th root of each one of those. Trying to use that property right there. So how'd you do? Let's take a look. So first answer. Here's what I recommend you do. Square root of 81 times square root of x to the 4th. think of that square root as being a little 2 right there, right? So square root of 81 would be 9, square root of x to the fourth would be x squared, so your final answer would be 9x squared, right? Next one. Cube root of a to the 12th. Let's multiply that by the cube root of b to the 15th. Let's use that trick. Take that 12, just divide it by that 3. What's 12 divided by 3? Yep, 4. And then 15 divided by 3 gives you 5. Awesome, right? That trick does work. It works all the time. So this last one right here, we have 4th root of x to the 12th, 4th root of y to the 16th. So that way we should have this answer right here, x to the 3rd, y to the 4th. Awesome. Awesome. Just awesome. Make sure you do that on your homework.